All right, scholars, picking up where we left off. So we started talking about sine and cosine as individual functions, obviously related to the unit circle, but as individual entities. And we've looked at their domain or the value of inputs from 0 to 2 pi. So this particular lesson is going to look at the negative or the opposite of the inputs. So negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. However, if we think to the unit circle, not much is going to change because the behavior is still periodic. We're just simply rotating in a clockwise manner. So we're going to interpret graphs of cosine and sine for input values less than 0. So we can interpret the meaning of angle measures less than 0 radians on the unit circle. And then obviously we'll know we've got it when we understand how to find the values of cosine and sine for inputs less than 0 radians. So we've had this windmill quite often in an earlier lesson. Let's assume that point P is at the point 1, 0, starting at 0 radians, and the blade rotates negative pi over 2 radians. P will be at the lowest point in its circle of rotation. That lowest point would be here. Color. There we are. Right, that would be the lowest value for P. In your own words, what do you think Priya means by rotating negative pi over 2 radians? Do you agree with Priya? Be prepared to explain your reasoning. I will have known whether or not you watched this video based on your response here. If point P is 1 meter from the center of rotation, what does the value of cosine negative pi over 2 tell us? What about sine of negative pi over 2? So if point P is 1 meter from the center, then we have a unit circle type behavior here for the windmill. So we should actually be able to interpret not a specific numerical value because we don't know how high this windmill is, but at least describe the new distance compared to the original point P. Now moving on to a clock, identify the radian angle measure that the hour hand rotates through if it starts at 3 p.m., right? So once again, normally we are typically, not typically, but the unit circle is done in a counterclockwise manner, right? Because that's kind of how we draw angles. We don't draw them the other way. Here, right, for 6 p.m., normally we would say that's a 3 pi over 2 angle of rotation. However, we're moving in a clockwise manner. Yeah, right, to go from 3 to 6. That's how life's been happening for thousands of years, or maybe hundreds. I don't know. Someone Google when a clock was created. So we would say that the angle of rotation from 3 p.m. to arrive at 6 p.m. would be a radian angle of rotation of negative pi over 2, which is equivalent to 90 degrees. So it is up to you to determine, and we spoke about this, I think, lesson 5 or 6, about this unit circle being divided into a certain number of equivalent sectors, which correspond to various points or angles of rotation on the unit circle. Quick hint here that if we are rotating a full 24 hours, or actually, sorry, we're doing 12 hours because we started at 3 p.m. But we started at 3 p.m., so that'd be a full 12 hours and 4 a.m. Your angular rotation must be greater than, actually, I'm not going to say. Must be greater than something, but think through that. And then describe your strategy that you use to determine the radian angle measure. So over the next few slides, we're going to be looking at the graphs of cosine theta, sine and theta, and them on the same graph. However, in the previous lessons, we looked at them specifically for positive radian values. Here, we're looking at them in negative values. So label any intersections the graph of the function has with the axes. That should be relatively straightforward. Right? We're going to be doing that on both. And then we'll be identifying the maximum and minimum value of the function. And we've done this in previous units. Okay, just because we're working with trigonometric functions doesn't mean that the concept or the meaning of those terms is going to change. And then what is the period of y equals cosine of theta, and what is the period of sine of theta? So in those two questions, if you've forgotten, the period is the length of the smallest interval that contains exactly one copy of the repeating pattern. I'm going to leave it at that. Think through the unit circle and that particular definition, right? It's the length of the smallest interval that contains exactly one copy of the repeating pattern. So what is the length or the distance that must unfold in order for the functions to repeat themselves? Hint, hint, it's between 0 and 2 pi. So looking at both of the functions together, select 2 points where they intersect. Yes, you can click on the points. I'm okay with that. But I would like to know the exact coordinate for the point. So notice how here we have set negative 7 pi over 4 and then 0.7071. Not good enough. You can actually tell me what that coordinate value is based on our properties of special right triangles. And then 2 more questions to wrap up, right? The y-axis is going to be a line of symmetry for one of the 2 graphs. Which one? And last but not least, what could be the value of cosine of theta if sine of theta is 0? So that's a conversation that we're going to have as a whole class. But when we select one of these values, I can't select it here because this is a drawing graph. Right, when we select cosine, sine is red. Okay. At pi over 2, sine has an output of 1. So we should be thinking, well, what is the output for cosine? And you can technically identify it in this graph. Okay. But you can also think of the unit circle. Right? What are the coordinates at pi over 2? Because those coordinates represent both cosine and sine, giving you 2 birds with 1 stone. And that's where we're going to take our 30-second pause before picking up together in class.